Thank you very much to the organizers for inviting me to give this talk on modeling the outflows of cool evolved stars. Some of the work that I'll show has been done over the years with collaborators, and I've put some here. I'd like to thank them as well, and many of the other people that I've worked with over the years. So although we've already heard red giants, AGB stars, red supergiants, they're losing mass via dense, slow stellar winds, typically 10 to 20 kilometers per second, and mass loss rates of 10 to the minus 4 to 10 to the minus 7 solar masses per year. The actual structure of those outflows can be very different in different systems. And we can see here, you can get very complex outflows. You can get spirals, you can get spiral structures, shells, bow shocks and tails, bipolar outflows, jets, all sorts of different kinds of substructure in these larger winds. And what I hope to do, I'd hope to comprehensively discuss all of the formation scenarios for these things, but I quickly realized that that's not going to be possible. And so what I hope to do in this talk is give you few examples of two cases: wind ISM interaction, so interaction with the interstellar medium and interaction with the binary companion, and show you through examples how modeling those interactions and modeling the observations can actually give us insights into physical processes that are important for stars and beyond, planets and even galaxies. So the way that we model these outflows, the winds, is through hydrodynamic simulations. We treat them as fluids. And these models, in the fluids, you need to have some equations to represent the physics. You need a solver to solve those equations. We can't simulate the whole universe, and so we need some boundary conditions, some domain in which we solve these equations. You need to set what your initial conditions in your gas are, and of course, because of limitations with computational time and also our understanding of the physics, there are lots of parameters and approximations, and therein lies the uncertainty. But I'll do a positive spin on it and say that, you know, this is where you can get quite richness of our models and a flavor for like our originality, creativity, as we try to approach these limitations. So the equations are pretty standard: conservation of mass, conservation of momentum, conservation of energy, and an equation of state. This is the sort of basis of all of these models. And then on top of that, you put in different physical processes. For example, in the momentum equation, you can have accelerations due to stars, due to point masses, gravity, radiation, pressure on dust. You can have heating and cooling effects that you see here with this lambda. And so you can add a lot of additional physics to these equations, but this is the basic equations. And then there are some basic methods that are used to solve these equations. You can have grid codes that use adaptive mesh refinement or moving mesh codes, as well as particle codes like smooth particle hydrodynamics. And these are different ways of approaching the solution of those equations on either a mesh, or you take particles and they represent some parcel of fluid. You can do 1D or 3D models. You can have different grid geometries. There are lots of different smoothing kernels. There are lots of advantages and disadvantages of these methods. I'll show examples of many different kinds throughout, but it's important to keep in mind that there are always capabilities and limitations of your models depending on the problem. So the winds that we're trying to model, I'm going to talk about the wind ISM interaction, the interaction with the interstellar medium in the case of runaway stars, and then I'll follow that with binary interactions. So when you have the interaction with the interstellar medium and a runaway star, typically what we do is we have a boundary condition where we inject a flow, your wind, that's at the surface of the star, so we don't model the star. You set your density, temperature, and velocity of your wind at that surface, and that expands away from that boundary condition, from that surface, and makes your outflow. Typically, in these types of simulations, we don't include any complicated wind driving. We just assume that it's a free wind, and that wind collides with the ISM. The interstellar medium is also modeled as a fluid flow, and so you have these two fluids that interact with each other. Often for computational purposes, we have the stars, we switch to a frame where the star is stationary and the ISM moves past. In the case where this relative velocity is supersonic, what you get is a shock wave when these two flows collide. You get the gas heating up, and that pushes outwards. You get a forward shock as the gas pushes into the interstellar medium, that's the bow shock, and a reverse shock as it pushes back towards the star, and that's the termination shock or the reverse shock. And using really relatively simple physics, you can actually get quite a lot out of these models and observations, comparisons. For example, the size of your bow shock, so the distance from the star to the contact discontinuity, the apex, that's known as the standoff distance, and it's set by the ram pressure balance between the two flows, so ram pressure balance of the ISM and the ram pressure balance of the wind. And you can see that you can substitute in here for the conservation of mass, and you can actually express the size of your bow shock in terms of the wind velocity, the wind mass loss rate, the ISM density, and the motion of the star through the interstellar medium. And so these bow shocks are very powerful probes, not just of the stellar wind properties, but also of the interstellar medium. They're important for a whole lot of other reasons. The material that passes through this interface is then sets the initial conditions for dust, for example, in the interstellar medium. That then is important for cooling down clouds, forming stars, forming planets. So it's important for a lot of different fields. It also is a great tracer, these interactions of variations both in the interstellar medium, so if the interstellar medium is changing, or the mass loss history of the star over time. And a really great example is Myra here that you see. This was detected with GALEX. It's a UV bow shock in the front, and this tail, this colossal tail, which traces tens of thousands of years of mass loss history of Myra. And what you can see is that there's, structure in the tail, and that's thought to be from Myra entering the local bubble. And so changes in the ISM will affect this, as well as changes in the interstellar medium. So this has been modeled quite nicely. And of course, if we have a good handle on modeling the bow shocks and what the velocities of the stars are, we can actually understand some of the origin of these velocities. So tying that to kicks in supernovae and dynamical interactions in clusters and around centers of galaxies. So it's important for a lot of different fields. And there are a lot of systems. And I imagine that as we have these large-scale surveys, many, many more of these systems will be found, these types of stars. And I should say that the observations really have improved a lot over time. This is IRAS, observations of Betelgeuse at 60 micron. And you can see how things have improved going to Herschel with PAX. And you can see these beautiful filamentary structures in Betelgeuse's bow shock. And you can start to resolve clumps and really have incredibly changed our view of these interaction regions. It's not just in the far infrared, although that's where the majority of these bow shocks are found. So, for example, R Sculptoris, but also, as I mentioned, in the UV, and there are increasing number of these. This is an example of CW Leo that was found, and these UV bow shocks tend to be for the faster moving stars, so 100 kilometers per second, 90 for CW Leo and 130 for Myra. And over the years, there's been lots of studies, really extensive theoretical and observational studies of these kinds of interactions. The first 3D models of this we used to show what happens when you actually have these interactions. This is for a star, like Betelgeuse, for example, that has a wind moving at different velocities and is making different assumptions for the ISM density. And you can see in the slower model, you get Rayleigh-Taylor type instabilities forming, and these finger-like instabilities grow, and you get clumps, and a very different type of morphology to the bow shock than in the faster model, which you see here at 70 kilometers per second, where these fingers don't have time to grow. You have shear between the ISM and the wind, and you get much more filamentary structures. And so the appearance of the bow shock, the substructure in the bow shock, will change quite a lot depending on your properties of the ISM and the wind. And this makes it a very powerful probe for the physics. Over the years, there's been lots of questions that have been addressed by the models. I think one of the open ones is still really what is the origin of the emission. So a system like Myra, which has emission in the bow shock from the infrared, so dust, and at the same time has, this really hot gas in the UV. When we do the models, we worked quite hard to really include a lot of different cooling mechanisms to try and get the temperature down. When you have these fast collisions, you expect 10 to the 5, 10 to the 6 Kelvin, so the gas should be hot, but somehow you manage to get things cool enough. There's some ideas that maybe the emission in the infrared is coming from the reverse shock, maybe material that's heated in the wind, and then the UV is from the forward shock. But I think that this is still a rather open question. What exactly is the emission mechanism in the UV, and also what is the location of these different things? Magnetic fields have been studied quite a lot. It turns out that depending on the orientation of the magnetic field, it can change the instabilities, it can stabilize them, for example. And then in the faster wind models, the hotter stars, it's even shown that the dust particles can actually gyrate around the magnetic field, and these gyro rotations can create regions that are denser and less dense, and so you can get filamentary structures forming. So this is nice work by Katushkina. And then there were these nice studies of different dust grain distribution sizes and what that does to the appearance of the bow shock. So the smaller grains tend to trace the gas, and you can see here the Rayleigh-Taylor instabilities, the contact discontinuity, where the larger grains seem to just move through the bow shock and not really be aware that it's this contact discontinuity is there at all. It seems from more recent modeling that indeed carbon stars require large grains, 2-micron size grains, but it's not clear what the case is for the oxygen-rich case. But really understanding what these grains look like at this interface and after the interface for these initial conditions for the ISM is quite important. The bow shocks themselves are very important because they set the initial conditions for the subsequent phases of evolution of the circumstellar medium. And so this is an example here from Eva Villaver, and this has been studied for what happens now if you have this runaway star and you then transition to the planetary nebula phase. Well, this is what you get for, you get a very different kind of structure if you form, oh, now I can't find my pointer and I have things in the way. Anyway, you get a very different kind of structure. I need to put the pointer on. Never mind. Okay, you get a very different kind of structure if you have a stationary star compared to a planetary nebula that's moving through the ISM. You lose a lot of that mass during the AGB phase. Is ram pressure stripped away as the star moves through the ISM, and so this is what Ava showed when you include the runaway stars. This is the case also for more massive stars, red supergiants, Wolf-Rayet stars. If you have a red supergiant phase before the Wolf-Rayet phase, you can get very different kinds of ring nebulae forming. And then, of course, these stars, they eventually explode. And so it's important for gamma ray burst, afterglows, and for supernova explosions, the appearance of these remnants. And so we can look at the observations, and indeed these have been modeled in some respects. So planetary nebulae in runaway systems. This is the Crescent Nebula. It's a Wolf-Rayet star interacting with a red supergiant, and then Cas A, where you have this orange glowing warm dust above it due to dust in the interstellar medium. Betelgeuse is a very interesting case, and this is an example where we can get new physics from studying these outflows. So we have the bow shock, which is the interaction with the ISM, but inside the bow shock, there's a static shell of about 0.1 solar masses of H1, and this material is basically just sitting there, and you need some method to confine it. You can't use interaction with the interstellar medium because we already know where that region is. That's ahead of it in the bow shock. But the idea that we proposed is that you can have some external ionizing photons, which can photoionize the wind inside the bow shock, and that can create a pressure which can confine this material. And so you can build up these photoionization confined shells. And you can store actually quite a lot of the red supergiant's mass over its lifetime. And this is really interesting for interaction supernovae. So this is an example of the luminosity of the supernova versus distance explosion. And in orange, what you see is a typical red supergiant explosion, a type 2P, and how it brightens and then eventually fades. But when you have this interaction with this dense material around, you get a re-brightening when the ejector hits that material. And so This is an example in magenta of a type 2N, an interaction supernova. And basically by confining this material, we can actually build up these shells, and you can see the types of rebrightening structures that you can get when the ejector interacts with it. This is interesting for a lot of different systems. These interaction supernovae are becoming more and more exciting. And it was thought that maybe it's, the red supergiant has, or whichever star is exploding has an outburst before it explodes. But in some cases where we have archival observations, we can actually see that this was not the case. And so we need some way to keep material close to the star just before explosion. Okay, so that's the wind ISM interactions. Now switching to binary interactions, so interaction of the outflow. And this was typically thought to occur, the studies have been analytic, and then early studies of just the accretor through some flow. And basically they derived a formalism, Bondi-Hoyle wind accretion. So this is standard wind accretion, where the companion moves through the wind of the star and captures some small fraction of it. The material collides behind the accretor, and you get an accretion column, and it flows towards the companion and gets captured. And of course, this is an example of the mass fraction, so how much material is accreted versus how much material is lost. And it depends on the orbital separation, that's A, depends on the mass of the companion, that's M2. So a more massive companion can obviously accrete much more material, it can gravitationally capture more material. Depends on the wind velocity, so slower winds, the star can capture much more material, and it depends on the orbital separation, so closer in, higher density material, and so you can capture more material that way. The way that these models have been done, the majority of them more recently have been not have included both the wind and the accretor. And the way that we do this is you don't model the star again. You have these free wind, freely expanding wind. You have a boundary condition at the surface of the star where you inject your flow. You can see the gravity here. So the two stars' point masses. This is MA. So you can see in the second equation. So here's the gravity, the acceleration due to the red giant, and this is the acceleration due to the companion. And basically, when you inject the flow, you inject it at the surface, and you assume that by some mechanism, the wind acceleration directly cancels out this gravitational deceleration due to the giant. And so you have this free wind again. And then you have some boundary condition where you remove material around the companion, because often we can't resolve the companion. And that way we calculate the accretion rate. This is a small, quick little toy model that I made to show what happens in the SVH case. So you have your star moving around, you have the reflex motion, which produces the spiral structure. This is the rendered density, this is the particle plot, and then you have the spiral arms that form the leading and trailing edges, and an Archimedes spiral. So the really pioneering models for this were done in the 90s by Tonzo. They put both stars in the domain, and they calculated, this is a slice of the flow structure in the orbital plane for two different cases. And this is this viewed edge on, so perpendicular to the orbital plane for very close binary 3AU. And they modeled the outflow and the interaction. In this case, it was adiabatic, and so you didn't see the formation of an accretion disk. But when they made it isothermal, then you can get your gas to actually cool enough that you can actually form an accretion disk. They modeled this in quite a lot of detail and found the focusing towards the orbital plane in these very close models, and that the flow structure doesn't look like standard Bondi-Hoyle type picture. Mastrodemus and Morris expanded the parameter space. They included more physics. They still have basically a freely expanding wind, even though they calculated in a different way. They calculated close orbits and very wide orbits, so close binaries and wide binaries. This is what it looks like face on. Again, you see the formation of accretion disk and spiral arms. And then for the very wide binaries, you see these Archimedes spirals. When you look edge on, then you see the arcs, as well as these bigger arc-like structures, and that the material in the wide binaries really is globally spherically symmetric with the sort of spiral arcs and the spirals and arcs imprinted on it. So this is what the 3D structure looks like, and many groups have calculated this over the years. basically coming to similar results, that these spirals are, the spacing between the spiral arms depends on the orbital period and the wind velocity. So you can imagine if you have a companion that's whipping around, you'll get very tight spiral arms. If you have a very fast wind velocity, then you have a lot of time to expand before the companion comes, and so you'll get very wide spiral arms. And so it depends on that. And also the mass of the companion determines the density contrast of the gas density in the spiral arm versus in between the spiral arms. And so a more massive companion will have a higher density contrast. It will be able to focus more material in the spiral arm relative to outside of the spiral arm. The mass transfer rates in these cases are typically the same or slightly less than Bondi-Hoyle type accretion rates that were found. And I remember showing this when I was calculating these as a PhD student, and a very senior astronomer saying, well, you know, these are very nice pictures, but you're not going to be able to do much with them because really, look, you're plotting log scale for your density. And so, yeah. And so I was quite despondent, but I happened to be in the right place at the right time. And I went back to my old talks, and yes, I was able to work. We were in Bonn, work with what I call ALMA superheroes, Matthias Melker, Walter Flemings, and Sophia Ramstedt. And we actually observed the first spiral with ALMA, and that was R Sculptoris. And this has really been a blueprint, I think, for many of our studies that we did afterwards, and for many of the studies that groups have done since. So basically, we were looking at the detached shell, but what we found was a spiral attached to the detached shell. And so this meant that R Sculptoris has a companion. We modeled this. We were able to post-process to get what the CO looks like with lime, so do post-processing radiative transfer. And going back and forth between the models, we were able to derive properties for R Sculptoris. This was with CO 3-2, and we did the same thing with a series of binaries. This is W Aquila. And what we found here were these arc-like structures on one side, and we proposed that this system is highly eccentric. And we ran, again, some SPH models, post-process with radiative transfer, and compared to the observations. And it turns out that indeed, even more recent studies by Tyser have also come to the conclusion that, yes, this is an eccentric, highly eccentric binary. So this is quite a good approach. And for R Sculptoris, there was the additional physics constraints that we got because this system has a thermal pulse. And so by going back and forth with the models and modeling the spiral, we were able to actually say what happens to the mass loss rate, the wind velocity during a thermal pulse, the duration of the thermal pulse, how much mass is in the shell, etc. And so it was a really big triumph, and I think we learned a lot about the physics from this system. And of course, R Sculptoris is not single. It has a companion, a hidden companion. We don't see it. We just see its signature in the spiral structure. And so this is a good way to detect small bodies around really, really bright stars that are doing all sorts of crazy convective motions. So you can't easily detect low mass companions around these giants, but perhaps their signature is a good indicator. And so in honor of the conference being in Australia, I do my little koala dance because this was very, very cool. So we got to thinking a lot more about what happens with these interactions with planets and brown dwarfs. And this is work that was done by my PhD student, Elias Saidi. And basically, we improved the models. We had, instead of just a constant outflow of free wind, we have pulsations. And those pulsations produce shocks, periodic shocks. This is what we expect from a single star slice. And then you have the planet or brown dwarf orbiting nearby. And the wake of that planet and brown dwarf interacts with those pulsation shock structures coming off, and they cause enhancements. So you can see an enhancement here, an enhancement there, depending on the resonance between the pulsation period and these shocks and the orbital period of the planet will determine how many times you interact with these structures. And so you can form multiple spiral arm structures. So this is what we're seeing in these movies. These are slices in the orbital plane. And you can see you can get 2-arm spirals. even 3-arm spirals if you get 3 interactions, and even 4-arm spirals. So you can get multiple spiral arms from these structures. Of course, if you have no resonance, you can get 0. If you have a very wide binary, you can get a single spiral, 2, 3, 4. So it's a very rich type of morphology that you can get by varying companion mass. So this is typically of a brown dwarf, few tens of Jupiter masses, and orbital periods. The pulsation period in this case was about a year. And whether we see this or not is still up for, still a question. I'm hoping that with the ALMA wideband upgrade, we'll be able to start detecting some of these structures eventually. It's very idealized. We already saw from the 3D models of the giant that, you have the material not coming off nicely in spherical shells, but I think that enhancements might still be there. So it will be very interesting to see. Regardless, the presence of these companions, these substellar companions, affect the mass loss rate quite a lot. This is a plot of mass loss rate versus time, and you can see, depending on the separation of the companion, you can actually change the mass loss rate by a factor of 2. And similarly, if you change, this is different companion masses, each line is for different companion mass, you can affect the mass loss rate by quite a lot. And that's quite important because a factor of 2 in the mass loss rate changes the AGB lifetime, changes your time for nuclear synthesis, return to the ISM, etc., and so will affect quite a lot of different things down the line. So these hidden companions are everywhere, and maybe even more than one, both on the AGB, red supergiant phase, and in the planetary nebula phase. There have been lots of studies of this. I think the record holder is this one. It's a planetary nebula. It has up to 5 stars in this, or 5 companions, 5 objects interacting. This VY-CMA has been proposed to be a binary where you have a low mass companion grazing the orbit and eventually spiraling in. The ejections seem to fit nicely what we see in VY-CMA. So this is recent work by Camille Landry. CW Leo, this new paper, is proposing that it's actually a triple system where you have a coplanar in a binary orbiting around, making the tighter spirals that we see inside the star and a larger spiral structure imprinted outside. So I'm going to skip some of this other information just to say we've had a lot of success with these free wind models in explaining the spirals. They have quite a lot of difficulty explaining the jets and bipolar outflows, just because you need to transfer a lot of mass. There's a lot of mass and momentum in the jets. And so that's kind of problematic. And then also when we include just standard wind accretion, Bondi-Hoyle type wind accretion in population synthesis models, progeny of AGB stars, so barium stars, SEM stars, post-AGB stars, there are a lot of problems. You need to switch to Roche-Lobe overflow in order to get the enhancements that you need, to get the mass enhancements that you need, but that circularizes your orbit, and what we see are highly eccentric orbits, but with strong enhancements. So you need a lot of mass to be transferred without circularizing the orbit. And so we propose a method called wind Roche-Lobe overflow, and that came from, again, studying the outflow of another type of system, and this is Myra. It's an interactive binary. It's an AGB star and a white dwarf companion, and at all wavelengths, it's seems to be very strongly interacting. Myra A's outflow is really strongly being focused towards Myra B, and this is surprising because the separation between these two stars is at least 100 AU or so. So it's on the order of 100 AU. It looks like Roche-Lobe overflow, but I put a little dot here. This is sort of the size of the star. And so it's not the star that's filling the Roche-Lobe, but rather what we propose is that it's the wind, the slow, dense wind of the Myra, which fills the Roche-Lobe and gets channeled onto the companion through the L1. And so it's wind Roche-Lobe overflow. And in this way, you can transfer a lot of mass. We generalize this for other types of systems and say that if you have your wind acceleration zone, that's a significant fraction of the Roche-Lobe radius. So here, then your wind will be moving very slowly, and you can really focus it, and it will fall into the potential well of the companion. if you have your wind moving quite fast by the time it hits the Roche lobe surface, so the wind acceleration zone is much smaller than this Roche lobe radius, then you can have something much more like Bondi-Hoyle. So we have these two kinds of regimes for the mass transfer rates. We wanted to model this, and in order to do this, now we really do need to move away from those free wind models and actually calculate this wind acceleration. So we do what was done with a lot of the 1D models. We have a radial pulsation, a sinusoidal piston. To do the radial pulsations, we get the shocks. And then here, instead of having this alpha equal to 1, we actually try and calculate the radiation pressure on the dust. And the way we do this for carbon-rich case, we use the moment method to calculate the opacity. And for the oxygen-rich case, we use dust tables. We include cooling and accretion as well in the models. And so this is what that looks like. This is the pulsating AGB star. You can see it's losing mass, and this is a companion. It's in an eccentric orbit. You focus some material towards the companion. It forms an accretion disk, but some of that material gets lost through L2, and you get these spiral arms forming. And so the structure looks quite different. Now, if we switch, so that was a close binary, and if we switch to a much wider binary, this is now 20 AU, you wouldn't expect such a strong interaction. We switch to the frame where we're orbiting around the stars, so the two stars are stationary, the co-rotating frame. This is the Mira, and this is the companion. And what you see is you do indeed get this dense material. This is a slice in the orbital plane of the gas density. So you get a lot of dense wind filling the Roche lobe and being channeled onto the companion, and then some material getting lost in a spiral arm. When we look at the dust and gas opacity, what you see is that you get cavities forming, as well as arcs, where you get enhancements and it's cool enough for dust to form, as well as these nice spiral structures. The key thing about this is that you transfer a lot more mass in much wider binaries. So you don't need to go to a 3 AU binary, but even for 10 AU, 20 AU binary, you can transfer a lot of material to the companion. And when you look perpendicular to the orbital plane, you can focus that material towards the orbital plane. And this is quite important for driving bipolar structures, for example, in planetary nebulae. We wanted to test this, and so we proposed again to look with ALMA at Mira. This is the CO322 data. Here's the AGB star, and this is the companion. And this is the same here. So this is the Mira, and this is the companion. And you see that many of the structures that we see in the CO, which traces the densest gas, is also seen in our models. So you have this extension here, and this arm, have this cavity, which we also have, this extended density here, and these spiral arm structures. There are structures that we can't reproduce that are not in the model, and this is at blue shifted wavelengths. We have these big holes. We think it's a bipolar structure. That's the result of the ionizing photons and wind from the companion. And so something like the work that's being done by Marie van der Sand on the impact of the ionizing photons and wind of the companion is important to now be included in these models. I think overall, the wind Roche lobe overflow models can explain a lot of different systems. This is another one that was not observed by a different group. And again, you see these cavities, spiral structures, and arms. So I think we're on the right track there. The mass transfer rates, as I said, are much higher. This is the mass transfer fraction versus the orbital period. In blue, you can see we ran a series of models for different separations. And in blue, you see what you get from wind Roche lobe overflow versus Bondi-Hoyle. So you can see you can get much, much more material transferred to the companion. And this has now been included in a whole series of different spaces, population synthesis, type of chemically peculiar stars, type 1a supernova progenitors. So you want to transfer a lot of mass to the white dwarf so that you can get it to Chandrasekhar limits. This expands the parameter space. And as I said, generalizing wind Roche lobe overflow, basically we said if the acceleration zone is a significant fraction of that Roche lobe, you can still get wind Roche lobe overflow. And that happens even in massive binaries with hot stars. And this has been shown in high mass X-ray binaries and has been used in population synthesis as well. So just to conclude and say, I think it's very exciting. the structures that we see around in the outflows are really beautiful, really complex, and they are produced by a myriad of interacting processes. Through these modeling classes, we've started to try and understand a lot of these processes, and through that we've been getting a lot of good insights into actual stellar astrophysics that have impact stellar evolution and planet formation and return to the ISM, all of those other things that come with that. We got new physics in terms of the photoionization confined shells, and also Windrow slope overflow, just from studying these kinds of structures with the models. I think, the models at some point have been leading, and for example, with the spirals and the observations following, I think we're getting to the point where now the observations are super and the models need to catch up. And so there's a lot more space, I think, for doing work on this. And so it's a very happy time to be working in this field. Thanks very much.
Hi, Shazrene. I really enjoyed your talk. This is Amanda here.
Hi, Amanda. I can recognize your voice.
Yeah, no. So in terms of the Windrow slope overflow, so it's interesting that you get higher mass accretion rates, but I see that the problem is still the orbital periods are still much too long compared to the barium stars. Have you thought about what's going on there? So in that final plot you showed, the orbital periods are still more than 1,000 days or 10,000 days. So they're still in the long part of the parameter space.
Yeah, no, I think that there's a lot of interesting questions. This was for circular orbits. It was for one mass ratio. So we have to run a whole, this is something that we're working towards. Really, to understand those problems, we have to come up with a good prescription, and we need many, many more models. And that's what we're kind of working on now. Sorry.
Okay, thank you.
Sorry.
That's okay.
Hi, Shazrene, Leen de Sen here.
Hi, Leen.
Hey. I have a short question for you, since it came back also to a discussion we had with Jolene Malfait earlier last week when she was successfully defending her PhD thesis, is that in one of your slides you have been showing the structures, and the last one, there were no numbers on the slides, was a very rectangular structure in one of those. And I can't, there were no numbers. I cannot point to the exact slide. Well, go back. Yes, that one, the rightmost one, and I think it was also in the previous slides. We also have seen that in Jolene's simulations, but then it came through that there was a problem with the energy that we put it in and the cooling there. And as of the beginning, we were a bit uncertain on the really rectangular structure, but I see it here again appearing. Is it numerics, or do you really think that's true what we can see there?
Yeah, I think it could be a combination. I think here in this case we didn't include any cooling, and so I don't think that could be the cause. I mean, I think these models in general with SPH are, they're very expensive. We're trying our best. We use millions of particles. It takes hours and hours to run, but resolution is a major problem for us. And so I think we can get some good idea of what the structures should look like, but the details, I think, are we have to run convergence models. It's expensive and it's really tough.
I know, I know it's the same here. But also, so Jolene, when she was including the cooling, then she got rid of the rectangular structure. Oh,
okay.
Jolene, you can comment on it, eh?
Yes, so indeed, I got this rectangular structure, but here I think is the rectangle caused by the pulsations, or are only like those four blue structures caused by the pulsations? Do you know? Is it because
No, it's not caused by the pulsations. It's caused by the interaction with the companion. So you see the blue structure is where you get this. Actually, in this case, not the density enhancement, the decrease in the enhancement of the structure. So I think it's the resolution around the companion and really getting that well. And I think when you add cooling, that helps you resolve that it changes your resolution around the companion, and that affects the outflow, I think.